intervals in real number line. The real number line can be written as a set where we use the set notation. X belongs to real number system. We can also represent the real number line graphically, where we draw an infinite line with an arrow, and then we mark the axis as X, and this is the real number line where each point is a real number. For example, we put some number 0 here, 1, 2, -1, -2, and maybe over here 3.5, and so on. Point on real number line, which is written as x equals 3.5, or as a set which includes one element. So the set X includes only one element in this case, and graphically we can represent this point by drawing the real number line, and exactly when X equals 3.5 we mark a point, so we draw a solid circle. Intervals on R. So the interval can be the entire real number line, it's a trivial interval, or a subset of the real number line. And we will start with finite intervals. Graphically, finite intervals are represented by line segments. We will start with open intervals, which is denoted by the symbol which involves parenthesis. So we write a comma b inside parenthesis, and as a set the open interval can be written as X belongs to R such that X is greater than A but less than B. So the notation with the parenthesis means that the points A and B themselves are not included in the interval. They are excluded, which is what we call as the open interval. So here A and B are excluded in the interval. So graphically, we can represent an open circle by drawing the real number line. And then at A and B, we draw an open circle. Here we drew a solid circle to include this point. And here to exclude A and B, we draw open circles. And the points in between we mark by a bold line. So I'm going to use another color. I'm going to take yellow. These are the points that are included in the set. Closed interval. Which is denoted by square brackets. And we write it as a set X belongs to R such that A is greater than X is greater than or equal to A, less than or equal to B. So here in this notation, A and B are included. So graphically, we represent these by drawing the real number line, then mark A and B, and we draw solid circles because we are including these 2 points, and also include all points between A and B. Half open intervals you can include A and exclude B. So we write it as A is included but B is excluded. So graphically we include A and we exclude B and include all points between A and B in the set. Similarly, you can also have the other combination where you exclude A, include B, A is excluded, B is included in the set. Infinite and semi-infinite intervals these are represented graphically by an infinite line. The first case is the entire real number line is an open interval between minus infinity and positive infinity. We will normally not put a plus sign, and you can also write it as a set minus infinity less than x less than infinity. So in all sets minus infinity and plus infinity are not included. So we will never include minus infinity or plus infinity in any sets. So this set can be, or this interval can be written as or shown graphically by drawing the real number line, and here we include all points. So we just color all points, draw a thick line to say that we are including all points on the real number line. Semi-infinite intervals. So we have 4 cases. We can include all points between minus infinity and a, where a is a real number and we are writing it as an open interval. So as a set, we can write it as x belongs to R and x is greater than minus infinity, less than a, where a is a real number. We can show this interval graphically by drawing the real number line, and then we take the point A. This point is not included, and we include all points from minus infinity until a. And the next case is half open interval, where we include a so where a is included in the set, x a, and now we are including a, so we draw a solid circle and all points to the left of a are included. Similarly, we can have the open interval a comma infinity and the half open interval, where we include a and include all points to the right of a. Okay, so we can draw diagrams for both of these cases. So in this case, we exclude a and include all points to the right, and in the next case, we include a and all points to the right side of a. We can also define a real number plane which we denote by the symbol R and a superscript 2 to convey that this is a two-dimensional space. So we write it as R times R. So here this symbol, multiplication symbol, is what is called as a Cartesian product. So what this means is we take a real number line between minus infinity to plus infinity, and you combine it with another real number line between minus infinity to plus infinity. Again, here the symbol, multiplication symbol that you see is the Cartesian product. The other way of writing this is an open interval x1 comma x2 and a product with another open interval y1 comma y2, where x1 and y1 are minus infinity and x2 and y2 take the value infinity. So this set can also be written as x comma y. So here the notation is a little bit confusing. You see here the parenthesis that we have used denotes an open interval, but in the next line this parenthesis, it denotes a point x comma y. So both x and y take all values of real numbers. So again, in this notation, this is a point. Okay, but this parenthesis denotes open interval. So graphically, the real number plane can be denoted by drawing vertical and horizontal axis. X is a real number line and y is another real number line, and R2 includes all points in this plane, so we just shade all points like this, which means that we're including all points in this two-dimensional space. Okay, this is our R. Let's see how we can denote a point on R2. For example, x comma y equal to 2 comma 5 are a set with one element. Is a set which includes one point, and graphically we denote this point by drawing the real number plane, x and y axis, and then 2, 3, 4, 5. We have 5 points in x and we have 5 points in y. 2, 3, 4, 5. And then x equal to 2 is here, and y equal to 5 is here, and our point is at the intersection here. Now let's see how to represent a line on R2. As a simple example, let's take x equal to 5, or we can write this as L to represent the line, which is a set of points in R2 x takes the value 5 and y takes all values in the open interval minus infinity to plus infinity. So graphically we can represent this line by drawing the real number plane with arrows, and at x equal to 5 we draw a vertical line, infinite line, and this is the line defined by our expression. We can do one more example. Another example, L equals points x comma y and R2 such that x plus y is fixed. So in this case x plus y equal to 1. We know that we can write this equation in a more familiar form, y equal to 1 minus x, and we can represent this line on the real number plane 6 y. We know that the line which has an angle 45 degree to x-axis is y equal to x. This is the y equal to x line, and the negative of that has a negative slope. This is the y equal to minus x line. This is the y equal to x line, y equal to minus x line, and then to this second line, y equal to minus x line. If you add a constant 1 to each point, so we had 1 here, and we had 1 here, and we had 1 here, and so on, and then you take all points, that gives us the line y equal to 1 minus x. Line segment on R2 which is another finite interval. So we take a line, set of points in R2 satisfying the condition x plus y equal to 1, and another finiteness condition x belongs to 0, comma 1, half open interval. We can also represent this line in the same way as the previous case, and x, y, and then in the last case we saw that this is how we represented the line y equal to 1 minus x, or x plus y equal to 1. Now we have an additional condition here. X equal to 0 is excluded, so this point is excluded, this point on this line is excluded, and x equal to 1 is included, so this is x equal to 1 on the same line which is included, and all points in between on this line are included. Now this is our line segment. Now let's look at two-dimensional intervals. Interval on R2, so that are areas, so we denote them as Cartesian product of two line segments. For example, we take 2,5 half open interval Cartesian product with 3,4 closed interval. So in this notation, what we have is an interval on the x-axis given by 2 points x1, x1, x2, and intervals on the y-axis with intervals y1, y2. So A is all points between these x and y intervals, 2 less than or equal to x less than 5, and 3 less than or equal to y less than or equal to 4. Now let's see how we can represent this interval on the real number plane. First, we'll start by writing down the corners of the rectangle. So we'll have to write all possible combinations of x and y, x1, y1, x2, y1, x1, y2, x2, y2. x1, y1 is the point 2, 3, x2, y1 is 5, 3, x1, y2 is 2, 4, and x2, y2 is 5, 4. Now we draw the real number plane x, y, and we mark the points on the x-axis 2 and 5, on the y-axis 3 and 4, and mark the corners so this is the area defined by the interval, and as you can see on y-axis the intervals are included, it's a closed interval. On the x-axis 2 is included. So in our diagram we include these 2 points are included while these 2 points are excluded from our interval. Operations on sets. We can also call them as operations on intervals. So these are operations that can be performed to convert one interval into another interval or to combine two intervals. Some of these operations are complement of a set, union, intersection of two sets, and set difference. So let's take an example. A is a half open interval between 3 and 5. 3 and 5. 3 is excluded, 5 is included, and all points between 3 and 5 are included. This is our interval A. Complement of A is denoted by the symbol A prime. A prime includes all points on the real number line that are not present in A. So we have the real number line, and 3, 5 are marked here. A prime includes 3 and it excludes 5, and it includes all points to the left of 3 and all points to the right of 5. So here we have two intervals. One is between -infinity to 3, and the other one is from 5 to infinity. So A prime is a combination of two intervals. So we denote it by the symbol U, where U stands for union. It's the union of two sets. Meaning it includes the union of two sets includes points from either sets or either intervals intersection So we have discussed union. Now let's discuss intersection. Let's take another example. A is from -infinity to 2, and B is 1, 3. So let's represent them graphically. We have 1, 2, and 3. So A includes 2 and all points to the left of 2. Say and B includes all points between 1 and 3, where 3 is included, 1 is excluded. This is B. So A intersection B includes points that are common to A and B. Let's draw over here. One, 2, and 3. So 2 is included on both sets, and all points between 1 and 2 are included on both sets. So A intersection B equal to half open interval 1, 2. So intersection is a set that includes points common to both sets. Set difference which we denote using a minus sign, a minus b, or sometimes a slash b. So this means points in A but not in B. So we will take the same example as before, A and B, as given in the previous case. So we have A shown here and then B shown here. From that, we can graphically represent points that are present in A but not in B. So that includes all points from 1 until negative infinity. So the points between 1 and 2 are present in B, so we are not including them here. So we are only including points that are present in A but are not present in B. So this is our set A minus B. So A minus B is the set from negative infinity to 1. You can also verify by yourself that this set is the same as A intersection of B complement. So this you can verify by yourself. Let's do a problem. We have 3 sets given A, B, B is between minus infinity and 6, and C between 4 and infinity. And let's find A complement intersection B minus C. So here we will have to represent the individual sets A, B and C graphically. So to do this, let's make sure that the smallest finite number among the 3 sets and the largest finite number among the 3 sets are shown clearly. So the smallest finite number is negative 3 and the largest finite number is 6. So let's make sure that the graph covers these points 0, 1, 2, 3, 4, 5, 6, minus 1, minus 2 and minus 3. The first set is between minus 3 to 4. Both the endpoints excluded, so we only include points between minus 3 and 4. This is set A, and set B is between minus infinity to 6. We have 6 here. So all points between minus infinity and 6 are included in B. C includes points from 4 to infinity, all points to the right of 4. A prime includes all points that are not present in A. So we can include -3 and +4 and all points to the left of -3 and all points to the right of 4. B minus C includes all points present in B but not present in C. So 4 is present in B, and not present in C, and all points to the left of 4 are present in B and not present in C. So from the last two cases, we can represent A prime intersection B minus C, which includes points that are common to A complement and B minus C. So which includes -3 and all points to the left of -3, as well as 4. So our answer is A prime intersection B minus C is -∞, 3, we include 3, union 4.